This is session KN4, Keynote 4. We have 4 extremely distinguished speakers today, so you're really lucky. I expect some tremendous presentations. I'm Bill Fisk from Lawrence Berkeley National Laboratory and my co-chair.
I'm Richard Didier from the University of Sydney.
Okay, so our speakers have asked for very short introductions so they can have a little more time for their presentations. So our first speaker is Dr. Matt Sandberg from KTH in Gävle, Sweden, and he's really been really a giant, I think, in the field of indoor air movement, air distribution, and related HVAC systems. So, Matt, please go ahead.
Ladies and gentlemen, I have the pleasure to talk for you about ventilation efficiency and laboratory studies. But before I can talk about ventilation efficiency, I have to talk about ventilation. So I will start with explaining some fundamental concepts. At least I interpret them to be very fundamental for ventilation. And a little warning, I also will show you some partial differential equations, but I will quickly pass over that part of my talk and then show real systems in operation. And at the end, I will hand out some challenges to you. So let us have a look on ventilation in work. This is a visualization made in the beginning in the 70s. It's a mock-up of an office room, and it's at those days, as John Sandberg said in the first day here, there were not any great interest in air quality. One advantage is that you can really do good visualization studies. The stuff that here used for visualization cannot be used nowadays. It's not too loud, but it's a very good visualization. And what we are studying here, or I was not involved in this, is we have a ventilation system here. It's called induction unit at the window, blowing air upward. The jet is hitting the ceiling and is dumped into occupied zone, and there's a risk of draft. And this was the interest in those days. Ventilation system, they were also associated with risk of draft. So, and I will start to try to explain what happens when in this encircled region, how ventilation works, how is this region ventilated. That's my purpose of the introduction. And something also about the flow. We have a very complex flow structures in here. The flow is dependent also on the boundary conditions, on the temperature on the walls, and there's slight variation the whole time. So it is slightly varying. And there's also typically there's recirculation, or call it for reflux. Okay, we are in the laboratory, so we start to make, of course, a laboratory study. So I will measure the flow rate in a duct in 2 ways. Either measuring the velocity profile with a velocity transducer, and this as velocity times area provides us with a flow rate. I call it denoted with velocity. Another method is to introduce a tracer gas source in the duct, release tracer gas at a certain rate, kilo per second, and record the concentration in this reading where I have uniform concentration. I put into this data the injection rate and the concentration into this equation. You see, this has the right dimension. It's a flow rate, at least by the dimension. And I will do this for 3 cases. The first case, I do have everything is flowing in one direction. It's always flowing in one direction, but there's nothing is coming back here. In the second case here, there's some black ones that are coming back. In the last case, everything is coming back. Then I use these two methods to record the flow rate. Well, if I use the velocity method, shown up here, in all three cases, 1, 2, 3, I get the same answer. This standard velocity measurement doesn't differentiate between how the state is with respect to what was in this duct. But we use the tracer gas method. Well, if I use, for this first case, the tracer gas method gives the same result as this velocity area method. If I then jump to the third case, when everything is coming back, then the tracer gas method gives an answer that the flow rate is 0. Because we don't, everything is coming back, this concentration, this is fixed, how much gas I inject, but the concentration increases, so it becomes infinite, and then the flow rate becomes 0. So we can conclude that standard velocity measurements does not discriminate between the three different cases. That's important information. So this leads us to, from the perspective of ventilation, fluid is a multiple population fluid. You have several populations that you have to keep count of. And that's also why we are using tracer gas methods and not using velocity measurements. So I had the, I have the population of never returning flux and I have population of particles returning. So, and what ventilates is, of course, I see, now it works. So, ventilation is the flow of particles never returning, leaving that region. So that's what is ventilated. And this part I call the purging flow rate. Flux of particles never returning. So that's a very important distinction to keep that in mind, that we have to identify the flux of particles never returning. Now we go back to this image I showed you in the beginning. So I have a look on what happens in this region, red region. I have a very complicated situation because I have particles that are returning and not returning. It's very, very complicated case. So I want to try to describe this a little bit in quite general terms. I don't have using any transportation terms. I just talk in terms of probability. So then one can plug in what kind of model for transportation as you like. So you look upon this in something like this. Just to find this, you have this control volume, have sides that crossing across each side in the positive direction and the negative direction. They call it forward crossing probability, and also backward crossing probability. And at each side, that is we take the difference between forward crossing and backward crossing. That's the escape probability, the probability to escape out of that side from the volume. And this you can, you can describe this in a probability term. That means that you have to also introduce probability for the particle to be in the volume. And you get a relation, a particle differential equation describing this in probability terms. And what was of interest to us to predict is the escape probability. That removes the contaminant out of the region. This is what we're aiming at, try to predict, to measure. So this is our target. And then you have to also introduce more or less, this escape probability, you write like this. I introduce a velocity. That's a net escape velocity. That's a stochastic transportation velocity for the contaminant. And then I will end up with the escape probability. That's the net escape velocity times the probability for a particle to be there. If you want this expressed in concentrations, it becomes this. This is a continuity equation for contaminant in that region. And this is, I refer to this paper in Journal of Fluid Mechanics, which inspired me to introduce these concepts. Okay, now I will show you an example. Now we'll leave the equations. Now in this case, we have predicted some colleagues in Japan the net escape velocity and the transportation. Spelling not correct. Transportation model is Reynolds average Navier-Stokes equations that anyone who's doing CFD knows about. But this is a model. And you can see here, we're comparing, we have a standard velocity, convection velocity called here. We have the net escape velocity. This one is a black arrow. And you see in observation that neither the direction or magnitude of the velocity and the net escape velocity are the same. They don't coincide. But this is the velocity by which a contaminant is removed from this region we have been studying. So this is what we have tried to predict and measure. I will come back to that later. So now we give you a more practical example of using this concept perdium flow rate. I ask a follow-up question, or we should ask ourselves, if you have a fan, is a fan flow rate that really ventilates a room? And this you can answer by using this concept. So here I have a room. It's just a room that's immersed in the ambient. You have a concentration in the ambient of the same contaminant that's generated within this volume. And this, of course, means if I do have this situation, the dilution potential of supply there diminishes. And this you can easily communicate about and express by using this perdium flow rate. Now I go back. This I do calculate. You have this emission rate and calculate the room concentration. And then I can express this perdium flow rate. And then you see this. I have given the concentration in the supply in this form. Here I had the perdium flow rate divided by the fan flow rate. Of course, if I do have zero concentration in the supply at this point, then the fan flow rate is the perdium flow rate. But with increasing concentration in the supply, I do have less than the fan flow rate that really ventilates. I think this is a good way of communicating about this problem. You can discuss here, should I introduce filtration to get rid of this contaminants in the supply? How much does it cost? I can express this in terms of the cost for the flow rate. So that's the idea of one idea of using this concept. Okay, now talk a little about ventilation efficiency. Air quality in a room is dependent both on how the room air is distributed and how the contaminant in the room is distributed. And these are some reference in the red I marked the reference values that dependent on the flow. And I don't see the red point. It's down here. You see, these are reference values that are totally independent on the flow. It's just continuity. What goes in goes out. And one way of quantifying how air is distributed is to introduce the age of air. Air is born when it arrives enters the room through the supply and dies when it leaves through the extract duct. And this is something you can measure. There are standards for this. I will not go into detail about this, but there is one important thing I want to point out. There is a relation between the mean ASO error at a point and contaminant concentration. Due to emission at each point, you emit contaminant at each point within the room. This is a kind of worst case situation. So you can use this concept, mean ASO error, to assess the contaminant concentration due to this emission source, which really is a worst case. Imagine you know, each point in this room, you generate a contaminant. Okay, what kind of air distribution? I said that ventilation or air quality is dependent on what type of distribution we have. Well, what kind of air distribution system do we have? Yeah, there are two types. There are also those controlled by the flow, high velocity flow or momentum, as I say technically, on those controlled by buoyancy sources, heat or we are heating or cooling. And for this system, there are two sorts. One is that really intended to work as governed by buoyancy sources. That's, for example, displacement ventilation. But many systems, they do work in practice like this. The airflow inside the room is controlled by the buoyancy sources. So that's a very broad classification of system. So when of course I'm talking about efficiency, what's the best air distribution we can achieve? Well, let's this case we have a piston flow. The air goes through the room like a piston. There's no reflux, no recirculation. Time to replace the air in the room is equal to the volume divided by the flow rate. That's the same time it takes to fill up the bath tube with this volume and this flow rate. So that's the most efficient system you can imagine, but very difficult to realize in practice. You try to do this in clean room technology, but it's very expensive. It's nothing for ordinary rooms, So, and these are examples of supply devices used in systems. That you have high velocity at ceiling level, you can use a high velocity. Then you can supply medium velocity impinging jet. That's another example of a impinging jet. And then at floor level, you need to have low velocities. And one example is displacement ventilation, low supply velocity, and the kind of flow is called a gravity current. So these are only some examples of what we use in practice. Well, let's see how works a high-velocity system. What are the characteristics of a high-velocity system? I have a room for ventilation flow rate. I have a jet. The jet in train air, so the flow rate at a certain section is higher in the jet than the supply flow rate. And this means that the net flow rate for the room, that's the flow in the jet minus in this reflux. There must be a reflux to compensate for this entrainment. So this generates a mixing within the whole room. So the air exchange efficiency of these systems, they are 50% when they work as intended. Well, if you start to heat, then the whole flow system is lifted upwards, and this is not easy to handle. I want to go back. I know you want forward. No. Now I'm back. Took some time. Well, if I heat, then the air doesn't penetrate into occupied zone. Of course, that's short-circuiting, and that's a very bad ventilation. Another case is that if I cool, then it may be so that the jet from the supply device is dumped into occupied zone, and that leads to people start to block the flow rate. So there's also a relation between thermal comfort and ventilation efficiency. So people's behavior should also be considered. Well, another called extreme is displacement ventilation. So I show some visualization here. It's done in water. I have at the fluorescent dye. Here you have heat sources down there and a heat source down there. I have a heat source in this case. It spans just a fraction of the height. I have a heat source here that spans the whole height. And you see that there are two layers. We have this non-polluted layer, clean layer down here. Here you have a mixing. So it provides supply air conditions at up to this height. There are differences between these two cases if you look upon the plume generated. Well, this is a plume generated in this case. This is a boundary layer, it's called. And what you have, look at the temperature profile, it looks like this. In this case, I have a jump here at this interface. The interface stops where the flow in the plume is equal to the ventilation rate. That's a fixed point. It's the same here. Here I have a boundary layer flow on this, along this heated cylinder. Then the layer stops here where the flow in this boundary layer is the ventilation flow rate. It's a difference in temperature profile between the cases. Here I have a step change. Here I have a gradual increase in temperature. And this gives a total different flows. And this is quite a standard flow that I think they're quite well known in connection with displacement ventilation. But in this case, I have, in fact, that's inversion. That you have an atmosphere. The air cannot penetrate it upwards due to this increase in temperature. And this leads to this kind of flow. You see the difference between these two cases. Here I have a lower clean region, and come to the interface, the flow along the interface. So here I have flow up the interface, and it flows along the interface. In this case, I have a mixing. It's a flow downwards towards the interface, flows along the interface. But in this case, I don't have a totally different case. I have inversion, so I do get, I call it side flux. You have these cells. The air cannot penetrate upwards. So it goes up, but it stops and it goes down. So this is inversion, exactly as you have in the atmosphere. But this is the example of ventilation controlled by buoyancy sources. It works also as controlled by buoyancy sources. I'll talk a little about what factors in practice do affect this air exchange efficiency. The number of factors. First of all, if you lose the primary air you supply, of course, then you have lost the ventilation air, of course, then you have a less efficient system. And I have measured the air exchange efficiency for these three systems. They're all for mixing system. 50% is a maximum, complete mixing. This system gives an air efficiency as expected, 50%. This system gives lower than 40%, and this is even less. So these two systems to the right, they do not work as ventilation systems. You should not pay for these kind of systems. They are not at all fulfill and decent requirements. So you can, and this is, I call it as a thermal condition, because here you have a loss of primary air. What you supply goes to the extract ducts and doesn't go into the occupied zone. So you don't know, it's no use of this lost air. Another thing, I'm not sure example of displacement ventilation. Systems are not always used as intended. Here are displacement ventilation. I saw you the pictures. You supply cold air at low velocity. Here I do we have heated air, and of course you get something rises upwards, but in trains air, so it works like a complete mixing system. It works quite well. With this location of the extract, no, I found it. But if I change the location of extract, move it up here, this I see in case in experience, then I'd have a direct loss of that. This is the worst case of short-circuiting I ever experienced. So that leads us to the following conclusion. You should talk about robustness of the system. I mean, systems do not always work as intended. So how do they work when, and then they work under non-design conditions, also something to take into account. How robust are the systems? That's an important question, or important issue. Well, that's another example. That's a chilled beam, normally supplying cold air, but now sometimes used during short times there's a need of heating. And these kind of systems that are used for providing warm air for heating. And this is not CFD. This is a whole field measuring technique showing the temperature distribution in the room. And you see all air is staying under the ceiling. So this is an example of a short-circuiting system. Well, another thing that in practice affects the air exchange efficiency is blockers. Sometimes there's a blockers in a room, so you cannot penetrate into the room there. I have still 5 minutes. Thank you for that. That's also a factor to consider. We have experienced such cases in practice. Entrainment is a basic mechanism for dilution. You entrain ambient air and dilute what you have in the jet. So this can keep that in mind. So if, for example, you constrain the entrainment, you have less efficient system. This I skip. And then here I show that you can see the performance of the system, how they work, by recording the air exchange efficiency. I show the air exchange efficiency 100% to complete mixing. Here I'm cooling on left-hand side. Here I'm heating on the right-hand side. Here I see the displacement ventilation and cooling has a very high air exchange efficiency. Here I see the contrast, the system that's short-circuiting. The air is just floating under the ceiling, very low air efficiency. So the recorded air exchange efficiency reflects the performance of the system. So it's a very good instrument for investigating particularly new systems that you don't know how they will work. And I come to my wish list. I will finalize my talk. I have some challenges. First, if there's a need to be able to record this net escape velocity, I tried, I failed. So I leave it to you to try to do this, because that provides very important information. I did have a system, a lot of tracer gas source in the center, and lots of sampling tubes around. But this was many years ago. The whole device was rotating. But I got a lot of very good information from the test, but it was a failure with respect to measuring the net escape velocity. Well, try systems that with flow variation. If you vary the flow rate, supply and flow rate, you generate a whole lot of secondary vortices that definitely improve the ventilation. You are getting rid of stagnation zones. And why do not, perhaps also a positive sensation of this type of air movement to people? Perhaps there's a vortice massage effect or whatever. So this, I think, is worthwhile to explore. And then I show example how we here, with particle image velocimetry, we can record the statistics, the vorticity statistics of this flow. But this is an example of a laboratory study, what you can do. And also, another wish I have on wish list, I suggest to analyze trajectories in the room, asking the question, a particle arriving here, where have you been? Have you been in a contaminated area? That's very important information. So you need to have different methods for recording trajectories. And then I find a question I'll ask you. I talk about net escape velocity for contaminants. Do you have an idea what's the net escape velocity for air? Is anyone who dares to guess? Okay, it's 0, because ventilation systems, they don't consume the ventilation air, but they do distribute the air in a more or less efficient way. So that's the end of the talk. I show another. This is hopeless, this one. Another challenge. Thank you.
Okay, thank you very much for that wonderful presentation.